In order to identify the most adequate solution here, we have to first select, as I mentioned before, a criteria for taking the decision. Because, of course, to different criteria correspond different decisions. This is a bit of a problem, of course, because the selection of the criteria is a decision in itself, and which must be agreed before taking the decision. Given that this is a decision in the decision, and it's a delicate decision in the decision, it's advisable that you select the criteria before showing the numbers to the involved persons. And I try to explain better. Ideally, the criteria should be independent of the final decision. So when selecting the criteria, you shouldn't have an agenda, as we say informally. You shouldn't aim to a given decision. The criteria shouldn't be influenced by the outcome from the decision. It should be independent from that. This is ideally. Otherwise, if you discuss the criteria among several stakeholders, of course, it's clear that each stakeholder tends to prefer the criteria that favors his preferred decision. This is clear. If you are debating for your right of using more water, and then you turn to discussing on the criteria, of course, if you have the possibility to make an evaluation, you would prefer the criteria that allows you to reach your target. In principle, however, it's clear that the criteria shouldn't depend on the final decision. The criteria, the selection of the criteria is an objective selection. So in order to make sure that it's really objective, it's better that you discuss the criteria before illustrating the various decisions and before showing the information that will allow you to identify the decision. Because otherwise it's clear that if you provide information, each stakeholder will try all the criteria and will identify what is the best criteria for him or her. So before showing the numbers, before showing any type of information, you should discuss with the involved stakeholders the criteria. So let me make an example of criteria so it's better understandable what I mean. One criteria could be to maximize the economical benefit, which means that you may quantify the economical benefit to each of the users, which of course will depend on the allocated water. So the benefit will depend on X1, X2, and X3. And then you could maximize the overall economical benefit. Which means that you maximize the benefit of the three users. And of course, if you don't show the numbers, then they will agree on that. But if you show the number and X1 understands that this criteria leads to an increased allocation to X3, then of course X1 wouldn't prefer the criteria of the max economical benefit. Because each user just pulls you to maximize, his target is to maximize its own benefit. So the economical benefit is usually a criteria that is chosen in water resources management. And if you want to discuss the opportunity with the users, the stakeholders, to adopt this criteria, again, you shouldn't show them the numbers that allow them to check if this criteria is favors them or not. Recently, there has been an increasing popularity of other criteria which are not easy to translate in terms of economical benefit. And for instance, one criteria is environmental preservation. And not always you can quantify environmental preservation with an economical benefit. And therefore, you may try to decide according to another criteria, like maximizing the population of fishes in the river downstream your water withdrawal. And of course this means that you don't take any water probably, but it's maybe not because maybe that there is a limit to the population of fishes that is dictated by other factors, other reasons that are not related to the amount of water that is flowing into the river. Or maybe that in some cases, if you reduce the water flow, then you reduce the water velocity and the fishes can reproduce more easily. So one criteria could be indeed maximizing the population of fish downstream. Now let's assume for what follows that our criteria is the economical benefit, because it's easy to deal with. But this is an assumption that doesn't take anything to the generality of the problem. If you have another criteria that it's the same thing, provided the criteria can be treated numerically, provided the criteria can be expressed through an analytical relationship that depends on your decision variables, then this is fine. So in general, your target is to identify a criteria that is equal to a function of x1, x2, and x3. And then you seek the optimum of this criteria in the same way as you identify the parameters for an informal model by optimizing an objective function, like the least square objective function. Then you select a strategy that allows you to find the optimum of this criteria. If the criteria is the economical benefit, it's clear what is your purpose, is to find a solution that maximizes the criteria, the economical benefit. Okay, so let's suppose that our criteria is the economical benefit, and we have an objective function that allows you to compute the economical benefit depending on the decision variables. And this objective function is indicated in the literature very often with the symbol NB, which stands for net benefit, depending upon capital X, which is the decision plan. So this is your objective function, which is of course to maximize you already have the means to find the optimum of a function depending on some parameters. In this case, the parameters are just decision variables. So that's fine. You already have the means. You know how to do it now. If you can translate the net benefit through an objective function, then you are done. Of course, this is not easy. This is a very complicated step in water resources management. Once that you define your criteria, and in this case our criteria is the net benefit, to express the net benefit through a function is not easy. This is a delicate step for which probably we need the support of an economist, or an expert in economy. But in some cases it is easy, because in some cases, let's suppose that you have to design an hydropower can sell the hydropower, and therefore it's reasonably easy for you to estimate the net benefit which derives from selling the energy. Of course, given that this is a net benefit, you have to subtract the costs. The net benefit function should include a cost part, which is negative. For increasing design flow of the hydropower, you get more costs. You get more money by selling the hydropower, but you get also more costs. Okay, so how can we then identify the best solution? And there is one simple way, not simple, there is one way which is analytical, and then there is the numerical way. You already know how to identify the optimum of a function by using a numerical approach. Basically, you have the d-optim function in R, and you can use that. But in many cases, you can also seek the analytical solution, which was much more used in the past for obvious reasons that I already mentioned to you, of much more limited availability with respect to today of computing resources. But I think that the analytical solution is still interesting because it allows you to better understand the mechanisms underlying the decision. So now I would like to dedicate, now about 20 minutes, some more. And then later on, next Monday, maybe a couple of hours in starting these analytical solutions before moving to, or let's say before mentioning the numerical solution, because the numerical solution you already know it. So basically now you would be already able to perform, to develop an exercise, to find the solution of an exercise. If I gave to you the objective function, net benefit function, and the constraints, you can solve it. Maybe that you are a bit concerned about the constraints, so how to impose the constraints, but indeed with d-optim, you already have seen that there is the possibility to put a lower limit to the parameter, and in this case the parameters are the decision variables, and an upper limit. So basically you have already some ideas for playing with it. Probably you still don't know how to impose this constraint, and we will discuss this. Okay? But let me give to you a suggestion. Let's suppose that now you are asked to, by using R, to find a solution of a problem like this. And you are concerned by this constraint. So the question is, how to impose this constraint in R? This is not difficult, because you may set up a trick to impose this constraint. What is the trick? You have a function, which is a benefit function, which you have to maximize. And of course, the minimum of this benefit function, okay, in principle doesn't exist because the benefit could be negative. But let's say that, of course, a benefit of 0 is something that you don't want to reach. So the trick could be that once that you try a combination of values for x1, x2, and x3, you know that the algorithm basically fixes trial values. And then, with this combination of trial values, the algorithm computes the benefit. That's fine. At the end of the computation, you may put an if instruction in your program code, which says if x1 plus x2 plus x3 is greater than q, then the benefit is automatically set up to 0, or minus 1000, whatever, but to a value which you are not interested in. And then automatically the algorithm will exclude all the solutions that don't meet the constraint. So basically what you do artificially is to introduce an artificial penalty to your benefit function. This could be a trick that you could use. You have to get used to these tricks because, you know, when programming, being able and experiencing with tricks is important. You may have only one doubt, which is, you know, what's the correct value of a penalty? So 0 is low enough to avoid convergence to wrong solutions, meaning with wrong solutions, a solution that doesn't meet the target. This is the only doubt that you may have. In this case, you know, if you put 0, you are reasonably sure that you avoid these solutions. But it's not so easy. Sometimes you may find that, okay, what is the penalty? What is the value of the penalty? So let's keep in mind, until next Monday, this trick and the doubt on the penalty. This is important, and you will understand why. Okay, now, as I said, I would like instead to focus on the analytical solution. And let me make an example now. And I'm just inventing the example, so let's hope that everything works. And let's suppose that the benefit function, so let's suppose that we have 3 decision variables, x1, x2, x3. Or let me say, to make it simple, because it doesn't change anything, x1 plus x2, 2 decision variables. So write again the example, because this is a numerical example that I am developing. And let's suppose that we have this constraint, x1 plus x2 is equal to q. And let's suppose I'm just inventing a benefit function now, mv capital X is equal to, just by chance, 12x1 minus x1 squared plus 3x2 minus 2x2 squared. I just invented it. So what do you see here? First of all, this is an objective function which is simple. It's simple because it sums to separate contributions, one depending on x1 only, and the second depending on x2 only. So this is quite simple. And you see that there is a positive in each of the components. There is a positive addendum, which is given by the benefit that you get from water, from allocating water. Remember that x1 and x2 are water allocations. But then there is also a cost term. And it's quite usual that the cost term, and you can recognize it because it's quadratic, because it's negative. It's quite usual that the cost term in water resources management is quadratic. So this is an example that I just invented, but I tried to mimic in a, let's say, in a reasonable and acceptable way the dynamics of benefit functions in water resources management. And given that it's quadratic, what you understand? You understand that there is a limiting value for x1 and x2, beyond which, if you increase the allocation, you reduce your benefit. So there is indeed a well-identified solution for this problem. Okay, first of all, let me forget about the constraint. So let's suppose that we don't have any constraint, okay? Just to make it simple for the first case. And then, of course, what would you do to find the maximum of this function? An easy way is to compute the derivatives with respect to x1 and put it equal to 0. And the derivative with respect to x1 is 12 minus 2x1. And then let me compute the derivative with respect to x2. And the derivative with respect to x2 is 3 minus 4x2. and this is equal to 0. And then very easily from each single equation you get that x1 is equal to 6 and x2 is equal to 3/4, I think. Yes, 3/4. Just check if I'm doing it, but I think it's correct. Okay? And basically x1 plus x2 is equal to 6 plus 3/4 is okay, is 675. Okay? This is very simple, nothing difficult. And but now let's say that we want to complicate our lives, and then lives. Yes, I think so. x1 plus x2 is equal to 5. This is my constraint. Now the question is, how can I solve it? Indeed, there is an easy way to solve this problem, and the easy way is given by the methods of the Lagrange multipliers. I guess that some of you are already familiar with Lagrange multipliers, because given that you have a very different background, and you know, I think that some of you already know this terminology, and maybe that some of you already remember, already know how to put it into practice. But in any case, I am introducing it now, and because the concept is interesting. The method of the Lagrange multipliers represents a very classical method in water resources management. And basically the idea is precisely the idea that I mentioned to you before. The idea is, in this analytical maximization, to introduce a penalty which is effective only if the constraint is not met. So the idea is, okay, is the same idea that I introduced to you 10 minutes ago. So how can I avoid that the analytical optimization converges to solutions that don't meet this constraint? The idea is, okay, if the solution doesn't meet the constraint, I introduce a penalty. As I said, which is effective only if the solution doesn't meet the constraint. So I have to write a new function, which is depending on the net benefit function, but with a penalty. So it's a new function. And this new function, which is given again by net benefit plus penalty, is called the Lagrangian. So let me indicate it with the symbol L, which depends on x, of course, and also it depends on a parameter lambda, which I am introducing now. And this Lagrangian function is given by the net benefit. So let me write again the same 12x1 minus x1 squared plus 3x2 minus 2x2 squared. This is the net benefit function, and then I have to introduce the penalty, with the condition that the penalty, again, is effective only if the constraint is not met. So let me put a minus sign here. A scaling factor which allows me to modulate the penalty that multiplies x1 plus x2 minus 5. So what do you see here? You see that the penalty is effective only if x1 plus x2 do not totalize to 5. And the penalty depends on the difference between x1 plus x2 minus 5. So it depends on how much, this is an informal way, how much the constraint is not met. And the penalty also depends on a scaling factor lambda, which is a means for me to be flexible, to modulate the penalty. And of course the question is, what is then the value of this lambda? Do you remember 10 minutes ago I said, the trick is to introduce a penalty and you may have a doubt. What is the right value for the penalty? So we are still wondering what is the right value for lambda. Okay, let's treat it as a variable. Okay, this is why I put here as independent variable of the Lagrangian, the lambda. Let's treat it as a variable. We are not sure on the proper value for lambda. Okay, let's assume that it's variable. And now what we have to do is to find the maximum of this new objective function, which is the Lagrangian function. And basically what I have to do is, again, to take the partial derivatives with respect to the variables and equate them to 0. There is one striking difference. I have one more variable, lambda, and so I have one more derivative. So let me compute these derivatives. Basically, derivative of the Lagrangian function depending on x lambda with respect to x1, it's similar to this one, is 12 minus 2x1 minus lambda, because there is an x1 down there, derivative of Lx lambda with respect to x2. This is 3 minus 4x2 minus lambda. And then the third derivative, derivative of Lx lambda with respect to lambda. This is equal to minus x1 plus x2 minus 5. All these derivatives are to be equated to 0. Good. Now, let me just manipulate these and let me, as I did before, let me derive x1 from this. So x1 is equal to, it's equal to 12 minus lambda. Let me think of it. Yes, 12 minus lambda divided by 2. x2 is equal to, it's equal to 3, okay, 3 minus lambda divided by 4. And then I have the last one, which is x. Yeah. x1 plus x2 equal to 5, which is again the constraint. Okay, let me write this one by substituting for x1 and x2 the relationship that I just derived. So I can write 12 minus lambda divided by 2 plus 3 minus lambda divided by 4, and this is equal to 5. Now I have only one unknown, which is lambda. I just need to make some computation to get it. So let me write in this way. Common denominator 4. I have 24 minus 2 lambda plus 3 minus lambda. This is equal to 5, which means that 27 minus 3 lambda is equal to 20. Which means that lambda is equal to 7 divided by 3. Fine, then x1 is equal to 12 minus 7/3 divided by 2, and x2 is equal to 3 minus 7/3 divided by 4. And these are our two allocations, but let me just try to check if their sum is equal to 5, because this should be our final result. So let me just write here in a different way, and this is equal to 6 minus 7 divided by 6, and this is equal to 3/4 minus 7 divided by 12. Now, x1 plus x2 is equal to 6 minus 7 divided by 6 plus 3/4 minus 7 divided by 12 equal to, let me put 12 here, 72 minus 14 plus 9 minus 7. So 81 minus 14 means 81 minus 14 is 67, minus 7, 63, divided by 5 is 5. Perfect. This is the method of the Lagrange multipliers. And be careful. The solution was fully analytical. So, from an analytical perspective, you don't have any doubt that the value of lambda is appropriate. So, the value that was identified for lambda, 7/3, is the right value that should be placed here. Be careful that there is a right value to be placed here, because if the penalty is too low, then you could identify solutions that don't meet the constraint because the penalty is lower than the increased benefit that you gain if you violate the constraint. So if you give more water to both of them, you increase your benefit, and you have to introduce a penalty that decreases the benefit properly. Otherwise, if the penalty is too low, you could anyway find solutions that don't meet the constraint. But the same applies if the penalty is too severe, because you may find solutions such that x1 plus x2 is lower than 5, which you don't want. So basically, the penalty shouldn't be too low, shouldn't be too high. There is a correct value for the penalty. And from an analytical point of view, at this stage, I am saying again that you don't have any doubt that lambda 7/3 is the correct value. Because we made a rigorous analytical derivation. And we checked that the sum of the two allocations that we found is 5. So, let me say again, from an analytical point of view, you are convinced. So your initial doubt, what is the optimal value of lambda, is solved. But